Hi and welcome to week 7. Couple of videos this week. The first we're going to look at exponential equations with E. And the second one is you finding derivatives of log and exponential functions. So up until now the logs that we've looked at have been base 10. And what we are going to look at is a number that Euler came up with. Euler over here was a mathematician, and using this sequence here we get a number that is 2.718281. It's just another common number, and we use that as a base of a number of logs. So just quickly, any expression can be referred to as an exponential expression. Properties with a base e are the same as those with base 10. So what we looked at last week, the laws, index laws, and log laws, those log laws still apply for the natural logs, which are logs to base e. And I've just mentioned here, expression log to base e is often referred to as the natural log. It's just written as ln x. So usually on your calculators, that is next to log, you have the ln as well, and it's just it's a log to base e, whereas log is log to base 10. So this is our general form, e to the power of m equals x. Then we can rewrite that as m, so the index, equals the natural log of x, where x is greater than 0. So we're just going to look at solving problems using natural logs. Now we could solve this equation here, or solve for x in this example here, of using logs to base 10, so the LOGs, take the log LOG of both sides. We can also use the natural log. So if we take the natural log of both sides, you can see that what you do to one side you've got to do the other. Then the 2x minus 5 index comes out the front, so we have 2x minus 5 in brackets log 3 equals log 7. These problems can be done, like I said, with the log to base 10. It doesn't matter, you just need to make sure what you do to one side is the same for the other. We can divide both sides by log 3 now to get an expression for 2x minus 5. So up here, add 5 to both sides, and then divide by 2 to get a value for x. So we can calculate that x in this situation is 3.386, and of course we are going to verify that to make sure we've done our calculations correctly, and yes, it does come out to be about 7, given that we did a bit of rounding up here. So these problems aren't very different from what we've seen before. We're just using a different log, which has a different base on it. So all the things we looked at last week when we were solving index equations and log equations, they still apply here. We're just introducing another form of log. The second example we're going to look at today, if x equals 1 plus e to the power of 3 divided by 2, and that's the solution for log ax minus 2 equals 3, what is the value of a? So we want to solve for a. So what we're going to use is that given that e to the power of m equals x, then m equals ln x. So what we started with originally here, we can use the natural log of that and put that as the power of 2 Euler's number. So remember, e is just a number. It's what we looked at originally here, 2.718. It's on your calculator, usually down towards the bottom. So rewriting that as to a power of e, we can write ax minus 2 equals e cubed, and then we can rearrange this to get a value for a. Now we know that x is a value of 1 plus e to the power of 3 divided by 2, so we can substitute that x value in the denominator here, and when we do that, we can see that when we're dividing by this, all I've done here is put this over a common denominator, so the denominator part of that fraction I've put as a common denominator over its own fraction. So we have 2 plus e to the power of 3, and then when dividing fractions we flip them and multiply them. So we have the 2 plus e to the power of 3 both cancel, and we're left with a equals 2. So what we're going to look at continuing on now is going through some exercises that involve us to solve equations with Euler's number and with natural logs. What we're going to look at in the next video is finding derivatives of those equations that have logs, natural logs, and Euler's numbers in them.